So, GPU Reshape. So, modern APIs are incredibly powerful, right? But they're inherently complex, as evident by a lot of the presentations here. And the more complex something is, the more likely something is to go wrong. We typically have three questions. What went wrong? Where did it go wrong? And, well, how do we even know if something did go wrong? Sometimes it's easy to tell, such as a device removed. But sometimes it's not so easy. So, CPU side, we've got excellent validation tooling, specifically the standard validation layers. However, they're rather limited by the available data. What if the issue occurs due to dynamic data only visible to the GPU? This can cause undefined behavior, crashes, or worse, nothing on your machine, but perhaps on your colleague's machine. In this screenshot, some things arrive with the atextual addressing. Validating things like these is what GPU Reshape is all about. So let's talk concept, and it's rather simple, right? Before something bad can happen, we validate it. And if something bad did happen, we report it. And that's really all that there is. But before I sell you on a good deal of complexity, I first want to demonstrate its ease of use. So let's imagine we're launching an application from Reshape, and let's validate it with initialization validation, that any read is preceded by a write. Okay. And it detects an error. Let's take a closer look. Just go ahead and double-click it. And let's check out what resource was uninitialized. In this case, I think it was the depth buffer. Additionally, I'd like to validate for resource out-of-bounds accesses as well. Just right-click. There you go, on demand. And it seems that we are reading TA buffer out-of-bounds by quite a large margin. Now, at its core, GPU Reshape offers instrumentation as a one-click endeavor, immediately available without any integration whatsoever. It should just work. So, continuing this idea, we need to figure out what can go wrong, right? And the answer is a lot. Descriptors can be bad. We can have infinite loops. We can have nans being propagated across different shaders, race conditions, etc. And we're all rather used to fighting them at this point. So to begin validating, we need to figure out what form of validation we are. And there's quite a few of them. We can perform it statically or symbolically, but we're lacking some data, which leaves instrumentation, of which there's two. Now, GPU Reshape being an integration-free framework really doesn't leave me with a lot of wiggle room. If all I see is binary, I have to perform binary instrumentation. Now, luckily for me, people much smarter than myself have already proved the point. GPU Reshape actually started from the paper Vulkan GPU-assisted validation by Carl Schultz from Luna G. The whole idea is to take the left-hand side code, in this case some SPIR-V, and inject it with validation so that it looks like the right-hand side. In this case, we're validating the coordinates of an image load instruction. And we want all of this to happen without any user intervention whatsoever, user being your application. But it's a little bit easier to think about with source code, right? That's what we're used to seeing. Again, we have an image load operation, and we want to validate its coordinates against its dimensions, as seen on the right-hand side. If something went wrong, we report it somehow. What's interesting is that many projects actually have handwritten validation, and this is instead fully automated through GPU Reshape. Another problem is that what if the thing we're validating can cause instability, right? Then we need to guard the instruction. Again, this is just source code, and we only really want to execute this instruction if the validation has passed. I personally call this safeguarding. If validation did not pass, a dummy value is instead assigned. So we're beginning to get somewhere. Specifically, we're beginning to get a lot of permutations. What I mean by this is that if I was to naively instrument the binary that the application provides, I end up with a lot of implementations. One per API, one per backend language, DXPC, Dixel, SPIR-V, and so forth, anything that the future may hold. So GPU Reshape attacks this problem through a custom intermediate language named GPU Reshape Intermediate Language, or GRIL for short. The basic premise is that while backend ILs may have their differences, the concepts are mostly the same, right? A texture sample is still a texture sample, an addition is still an addition, and so forth. So let's have a common form where we'll be able to write once and instrument everywhere. Specifically, GPU Reshape can be seen as a two-front abstraction. On one hand, we have the APIs, and on the other, we have GRIL. Each serves as a functional abstraction for all API particularities. And to make sure I'm going in the right direction, GRIL is heavily LLVM inspired. That is, it's single static assignment, very strong typing system, a set of functions, basic blocks, instructions, etc. It's not really important to understand all of these tiny details. What's most important is that all instrumentation happens on GRIL only. There is exactly 0 API visibility. GRIL is a common form IL that allows for bi-directional translation to and from the backend languages, SPIR-V and Dixel and DXPC. And on top of this, we've actually hand-rolled custom parsers and compilers for Dixel and SPIR-V, specifically written for instrumentation. Translation, interestingly, does not go through any other intermediate representations, so it's highly performant. It takes the binary IL, translates it to GRIL directly, and then back to binary IL, and then finally to the driver. But a full backend language abstraction is not the goal, and it would take far too long. What GRIL instead does is that it exposes a meaningful subset of each language with the behavior of the unexposed constructs maintained. For example, let's say you modify an image load operation which has unexposed instruction operands. You change the coordinates for whatever reason. The behavior of the unexposed operands is kept intact. And trivial differences in instruction sets, that be address spaces, differences in instruction, the actual instruction set itself, etc., are abstracted away for you. You don't really need to worry about that. Interestingly, certain instructions don't actually have any direct translation between the intermediate languages. Reshape abstracts these operations with what I call symbolic instructions, which are essentially fake instructions that unify behavior across the backends. They don't actually have any semantic relevance. One of such examples is the binding model. It's arguably one of the biggest differences between the APIs, which also applies to the intermediate languages. In this case, in the code here, the Dixel create handle from binding is represented as an address chain and a load. Only the load is actually recompiled. The former is symbolic. This allows for a unified representation between Dixel and SPIR-V. But language paradigm differences are another story entirely, and two in particular. We have what's known as scalarized versus vectorized representations and structured and unstructured control flow. What GRIL does here is that it infers when it can and exposes when it cannot. So the first paradigm difference, SPIR-V is a fully vectorized form, whereas Dixel is a fully scalarized form. GRIL chooses to follow a fully vectorized form because it would be far more work to fully scalarize SPIR-V than to just scalarize any changes to the GRIL instructions. These snippets demonstrate what's happening. On the left-hand side, we have a vector addition, which simply gets scalarized down to its individual components. And this applies to any vectorized operation. The backend, in this case, the Dixel compiler, will infer everything for you. You don't really have to do anything. Another difference is what's known as control flow. Now, I'm going to keep it simple and say that structured control flow is a very strict set of requirements on branching, where flow is sort of the order of operations within a program. SPIR-V is a structured format, Dixel is not. And imagine Dixel as a bunch of go-tos and jumps. The thing is, inferring this is very difficult and dangerous, so it's instead exposed into the language. In this screenshot, we're performing a branch to one of two blocks, and we inform the backend where these two paths will later merge on. If the backend needs this information, it'll use it, and if not, it'll just discard it. But control flow is a bit of a funny creature, right? What if the feature needs structured information? Like in typical HLSL, JLSL, this could be a for loop, a while loop, but that's just in source code, right? In IL, it's just a bunch of basic blocks branching through each other. We have an entry point to the loop, and then somewhere there's a cyclical branch back that's known as the back edge. The thing is, backend languages may not have this information, so we need to reconstruct it. And while this particular thing isn't very hard to reconstruct at all, the point is that the necessary tooling is provided to reconstruct such constructs, including loop trees. And lucky for me, there is plenty of literature on it, right? It's a solved problem, just have to implement it. And a bunch of other things. We have binding models, type representations, constants, metadata, and so forth, right? Now, personally, I love this stuff, but really the important bit is that given compliance with this backend language, translation to the associated backend IL is seamless. It'll just kind of work. So instrumentation in and of itself is half the battle. The features never interact with the APIs themselves, so that has to be abstracted as well. And think of Reshape as a collection of building blocks. On one hand, we have the API abstractions, such as data streaming, descriptor management, etc., fence management, everything you can really imagine, right? And on the other side, we have essentially standardized functionality using these abstractions. This may be commonplace GRIL manipulation, where GRIL is the language, or analysis of shader operations. There's a lot of stuff here, right? But I briefly wanted to go over some of the things that it offers that I find interesting. We know the concept, but how do we actually get any data back from the GPU? Reshape offers a single-line GRIL instruction named export that handles all of that. All the memory layout, interoperability, streaming, synchronization, etc. is automatically handled for you. You just call the function, and the data will find its way back. Another one is descriptor management, which again is one of the biggest differences between the two APIs. But usually features, or validation rather, just want an ID and a little bit of metadata. So enter what I call resource tokens. They provide a global ID for you and a little bit of metadata about the resource, such as its type. This is also exposed as a one-liner through what I call resource token emitters, and implementation-wise, it gets compiled down to and this is register-wise, it's not the previous scalarization, a single vectorized instruction and a couple scalarized, so it's crazy fast. And with this, most features can do their work. On top of this, there's a thing I call feature programs. What if you want to write your own shader? Do we write them in HLSL, GLSL? Why not just keep the same programming model? Just write the shader entirely in GRIL. This essentially allows features to manipulate state independent of shader operations, which is another powerful tool that validation can take use of. And with that, we have a very lightweight command abstraction. Before any pending shader operation, you may wish to inject commands, upload data to the pending invocation, etc., or even execute feature programs. It's really up to the feature. Anything it needs, launch its own command buffers, etc. Typical abstraction stuff. So that's a lot of different things, right? So let's talk about how they're actually used today and how we really validate things. So most features follow the same doctrine. We find all the instructions that can cause issues, we validate them somehow, and then we split these blocks according to needs, since we now need to branch. Again, a block being like an instruction stream. If a fault was detected, we branch to the error block, which then exports some data, and if not, we just resume the program. Pretty simple stuff. But what about safeguarding? We add an additional block, and we move the dangerous instruction to this guarded block. If an error has occurred, we assign a dummy value. Now, to select the actual value, we use these things known as FIA instructions. I just think they're neat, so I just wanted to mention them. Just think of them as ternary operators that selects the resulting value based on the previous branch taken. Dummy if it came from the error block, and data if it was valid. So that's really the entire doctrine. So let's talk about validation, and specifically let's talk about resource bounds. It's the validation that any texel or element addressing is within bounds of a particular descriptor. This applies to buffers, structured buffers, and textures. Luckily, hardware supplies most of the functionality. We just query the resource dimensions in shader, and if any index is larger than its given size, we have an error, and then we export all the relevant data. Now, other than a bunch of basic block handling and tedious work, this is really the bulk of it, right? This is the secret stuff. Another simple feature is the validation of floating point stability. This happens on UAV writes, render targets writes, and interstage data like vertices, which is quite applicable to mesh shaders as well. The test itself, we just check if the value in any given dimensionality, again, GRIL will handle vectorization or rather scalarization for you, is either infinite or none. And if either, we got an error. So it's nice and simple. Invalid descriptors, not so much. It's a rather easy way to crash the GPU. They've gotten better, but still, you know. They may be undefined. They may be subject to out-of-bounds indexing, such as bindless. You may have a mismatch between the compile time type to the runtime type. You create a descriptor in one thing, the shader expects another. Or you may be missing the table binding entirely. Now, enter resource tokens. Like, again, this abstraction just provides you everything you need in order to validate things, particularly as it's a guarded operation. So if you call it with an index of 1,000,000, don't worry. I mean, it's going to figure it out. And from this, we essentially validate if there's a mismatch between the what's expected there and what's actually there. Now, there's a couple more things needed, but this is the most important bit. On top of this, we also protect against crashes, meaning, or rather, to protect against crashes, we employ guarded validation. All of this just sort of happens. And now that we know that the descriptors are valid, what about the data inside of them? Let's validate that any read was preceded by a write. The problem is there's a lot of ways resources can be initialized, both from command buffers and shaders themselves. On the feature side, we essentially have a very large buffer with initialization masks. And these masks are very recently now tracked on a per texel or element level. And the resources essentially sub-allocate into this buffer with very carefully managed textual addressing logic, which we have to write in software. And that's an interesting problem space. And we're also limited by typical 32-bit addressing, but this is greatly helped by the fact that we keep it 1 bit per texel, meaning initialized, uninitialized, and then a bit of atomic addressing to keep things thread safe. One problem, though, is that initializing this mask has to happen in a shader, for the reasons being atomic initialization. And if we're inside of a shader, any user read will essentially just validate the mask, and any write will atomically assign the relevant bits. Okay. But command buffer writes, such as clears, copies, etc., actually launch a separate kernel to set things up, and it does so with these feature programs. But the thing is, what if a resource was initialized on a transfer or a copy queue? I can't really launch my queues here. The thing is, when Reshape is enabled, it'll actually emulate these queues for you. They're just regular compute queues. You don't know, I don't tell the application, it sort of just happens. But even if there's data, maybe it's concurrently being read and written to, a race condition. So let's try to detect that as well. At most, we know that there can be a single producer or multiple consumers. As with initialization, this is tracked on a per texel or element level, on a bit-by-bit basis. And this essentially works by assigning lock guards on writes and then validating the active lock on reads. If either the lock failed on writes or something has locked a particular range on reads, we've got a race condition. One important note is that today, race conditions between command buffer operations and shader operations, such as you clear a buffer and use it at the same time in a shader, are not detected. And additionally, it's important to note that this is not a hazardous check. This is, as with all other features, it is reporting what is actually happening. So, okay, descriptors are good. The data is valid. It's probably thread safe. But sometimes there's hardware particularities. And one of these things is called waterfalling. The thing is that dynamic register indexing of both S and VGPRs have to be serialized in hardware. This has vast performance implications. Typically, if neither the data accessed, such as an array, a VGPR array, or the indexing into said data cannot be deduced at compile time, and the index is potentially, and this is at compile time, potentially divergent across a wave, we need to serialize the addressing. If the data is constant, we can move it to global memory. The compiler does this for you. And if the indexing is constant, we can try to inline the element. But what is waterfalling, right? Let's go over it. And mostly it's one of two forms. For smaller data types, it's essentially a set of conditional masking instructions. These aren't free, but they're not overly expensive. However, for large data types and descriptors, enter bindless, it compiles into an actual loop in the ISA. This loop reduces the execution mask to such that each iteration only handles a single unique value at a time, and this can be very expensive. Validation, though, is not easy. On the compiler side, this is resolved through a lot of optimization passes, and we want to get as close as possible to it. So we employ what's known as conditional constant propagation, which basically figures out what can be computed at compile time and what value it has. It's a surprisingly not easy topic. On top of this, we extend it to handle local memory operations such as loads and stores, and simulated loop propagation as well. But we in this case actually chose to keep it in one. And from here, the validation checks if either the data or the index may be constant folded, and finally, if the value is divergent across a wave or not, by analyzing divergence throughout your shaders. It's important to note that there are exceptions to this, but it's a really good estimate, and it's already caught a few issues in some samples. Additionally, it's very trivial to extend this to detect missing non-uniform resource indexes. As you know, if you have a descriptor array and the value is divergent, it has to be annotated. The driver will generate much needed waterfalling here. Otherwise, it'll assume uniform indexing, which, if incorrect, will result in really hard to diagnose problems. Reshape validates this by checking any value that is assumed uniform within a wave is actually equal. And if not, you get an error like above. And finally, loops. We also want to guard against both infinite loops and TDR causing loops. The basic idea is that we want to allow the application to escape the loop before a timeout may occur. On the CPU side, we essentially have a heartbeat thread that monitors all active submissions and signals for termination if any particular submission has exceeded the elapsed threshold or the elapsed time of which there's a threshold. GRIL side, each loop header, which is like the entry point again, is modified to atomically read a signal on each iteration. If the signal is set, we escape the loop. For unstructured programs, we need to reconstruct the loop trees. Again, GRIL, it's a one-liner, it does it for you. And additionally, things get a little bit complicated regarding these FI instructions since there's now an additional way to escape the loop. All of this is functional today. But an interesting problem space here is that there's actually an unsolved problem, and that is getting CPU-fed data to a running shader, right? Turns out there's no specification-proof way to make this happen as of today, so we make architectural assumptions because of it. Additionally, we also employ a per-thread iteration limit as another safeguard. Basically, you have an additional counter per loop that's incremented on each iteration, and should this counter exceed some configurable limit, we're going to terminate your program for you. In fact, we actually terminate all future loops as quickly as possible to allow the whole command list to pass, to ensure like that the GPU, again, can escape a potential TDR, because the moment that TDR kicks in, we're not getting any data. It's important to note, however, that this does not prevent any side effects from happening, such as if you have any external memory operations going on during this erroneous loop, that'll still happen. But features themselves are not infallible. Take resource-bound validation. It's querying the dimensions of a descriptor on the descriptors, right? So it needs valid descriptors, and if it's invalid, the GPU will crash. The way this is handled is through what I call hierarchical instrumentation, and it's basically that features have dependencies on other features. In this case, resource validation depends on descriptive validation. It's easy enough. Descriptive validation runs first, guards the instructions, and then resource bounds uses the already validated descriptive data in the guarded path. And this is a really convenient way to reduce the amount of work needed by each feature. So that's kind of it on my part for now. A lot of setup, and I'm going to pass it to Lou.
Yeah. Thank you. So now we know what Reshape is, but let's look at Reshape from an end user perspective and how to actually use it with your application. So GPU Reshape, you can find it on gpuopen.com. There's the product page, and there's also the link to the GitHub repository where you can just download GPU Reshape. It's all open source. And you will also notice that there are a lot of different branches, actually, because development is happening in open source. And the structure is that new features and bug fixes are developed on separate branches, and once they're stable, they're merged into the development branch. These branches, they don't have pre-built packages. Pre-built packages only exist for official releases, which are on the main branch. And these are just ready to download. And here you also find the link to the latest official release. If you want to get a more recent version of GPU Reshape, for example, from the development branch, you have to build it yourself. And in theory, it's quite simple. So there's a BAT file to generate the Visual Studio solution. Then you just open it, build it, and then you have the binary that you can just launch. What's important to know is that the building process will pull automatically all third-party dependencies. And this can lead to some issues depending on your IT security system. So be aware that this is happening so that you also know where to look for if there are issues. Also, one thing to notice, because several people have been asking this, but GPU Reshape is working on all GPU vendors, so it's not AMD specific. It also works on other GPU vendors. If it doesn't, then this means there is an issue, so please open a GitHub issue so we can fix it. So, but if you have GPU Reshape built, then just click on the executable and the GPU Reshape UI will open. So now the question is, how can we connect GPU Reshape to our application? There are two ways to do this. One is via discoverability. By default, discoverability will be disabled, which can be seen on the small icon on the top right, which is yellow, which means it's disabled. And you can just click on it and then click Start Discoverability to enable it. So what is discoverability or discovery? It basically tells GPU Reshape to actively listen and to detect newly launched DX12 and Vulkan applications. It already hooks into the application at this point, but it doesn't do anything. So it will just forward all the function calls. So no instrumentation is happening at this point yet, but GPU Reshape will know, okay, a new application will be launched. Already running processes will be ignored. So once discovery is enabled, then you still need to create a workspace. So you have to basically have this extra connection step within GPU Reshape and your application. So you can do this either by just clicking on the workspace creation icon or go to workspace and then click on create connection. And then the window will open that will list all tracked applications that you can connect to. And then you just connect to them and then you have a workspace. And this is how it will look. So then you will see that the workspace is created. So you might have noticed when you were enabling discovery that there's also a so-called global hook, or also called global discovery. If you click there, it will install GPU Reshape services. And services basically enables GPU Reshape discoverability on system startup. So this makes sure that GPU Reshape tracks all your applications automatically without you manually remembering to enable discovery. This might be useful, for example, if an artist is working on a new effect and then suddenly artifacts appear on the screen, and then you can just remotely connect to the machine and create a workspace, because GPU Reshape will have been actively listening and will be aware that the application is running. And this is especially useful if the issue is difficult to reproduce, because it means you do not have to relaunch the application. But of course, before you enable global discovery, make sure that it's actually compatible with GPU Reshape so that you don't run into issues. So the second way to connect with an application is that you also can launch applications via GPU Reshape. So it's very similar to the workflow that you are used to when using Pix, for example, or RenderDoc. So you just go to Workspace and then launch applications, and then you just provide your application path, and then you can just launch it. If you go this route, you actually have additional options that you can provide. So you can enable safeguarding that Miguel was talking about. You can also request detailed reporting. So depending on the feature, you will get even more information than the usual reporting would give you. And you can also enable synchronous recording. Actually, synchronous recording is required for the initialization feature. And if you have the initialization feature enabled, it will force enable synchronous recording as well. And this is also the main reason, I would say, why you would want to use this launch application feature, in case you want to use the initialization feature, because it's required. So, but now we have a workspace created with our application, and now we can start instrumenting. There are different levels of granularity where you can instrument. You can just do a global instrumentation, and then it will show all the messages on all the shaders and pipelines that are in your application. And it will instrument all existing shaders and pipelines, but also all newly created ones. So for example, if you're in the main menu, you hit global instrumentation, and then you load into a new level, you will see, okay, all new shaders and pipelines that will come in will also get instrumented. And you can see all of this in the log file. So of course, for some applications, this might be too much, because some applications have a lot of pipelines. So it might be better to just instrument specific shaders or pipelines, and this is also possible. Then just right-click on the specific shader and click Instrument. And then you just see the error warning for the instrumented shader. And you can also switch between shaders and pipelines. You can also filter for specific pipeline types, so either graphics pipeline or compute pipeline. Sometimes instrumentation fails, and if it does, then you can inspect the log to see why it failed. And one example would be that it has been the bytecode, because right now the bytecode is not natively supported. So in this case, you can actually try to convert it to Dixel. So you just go to File, Settings, Applications. There you click on the plus sign, you enter your application, and then the name. A substring is already enough. And then you select the application, and then you just say, okay, you want to do the Dixel conversion. And then GPU Reshape will instrument the converted Dixel code. Sometimes the conversion itself fails because it's using dixelconf.dll. And since GPU Reshape has no control over this, there's nothing GPU Reshape itself can do. Here, you might have seen in this screenshot as well, here you can also set the symbol path. So if you have external PDBs, this is also where you can set the path, so GPU Reshape can find them, in case the PDBs are not embedded in your application. And then once instrumented, if you want to get details, yeah, you just double-click on the message, and then you click on the message here once again to get further information if available. So that's very broadly like how you use GPU Reshape. Really, there's nothing more to it. Here's a small case study for a case where GPU Reshape used to be helpful already. So we had an application that crashed on an AMD RDNA 2 GPU, but it actually was running fine on AMD RDNA 3. And then we got the idea, hey, we can just run the application on RDNA 3 and see if GPU Reshape reports something. And it actually did. It detected an out-of-bounds descriptor indexing and also pointed to the line in the shader source. And with that, it was quite easy to fix the issue. And once fixed, also the crash on RDNA 2 went away. A small note here is actually that we could have tried to run the application RDNA 2 with safeguarding enabled as well. In theory, this should have worked, but we just weren't thinking about this back in this time. But this is also something you can try out, especially if you don't have a GPU where the game is not crashing. So, but now we looked at GPU Reshape as a standard user, but we can actually go one more step. Because as Miguel already explained, GPU Reshape is built in a way that's very modular. So features are just plugins that GPU Reshape just loads. So this gives us actually the option to write our own features. And I want to walk you through a very simple example of how you can write your own feature. So of course, which feature we want to write. So let's first talk about our example feature today. And since we all should know by now that mesh shaders are great, the feature will be mesh shader related. So this conference alone has 3 talks about mesh shaders. One was just the hour before. There will be 2 more tomorrow. One will be by my colleague Łukasz. We will talk about mesh shaders, but also about work graphs. So I recommend everyone to attend it. So for this talk, I will just talk about one very specific topic, and it's because on AMD RDNA we have this recommendation that the mesh shader thread should export the vertices and primitives with the same index. So thread I should export vertex I and primitive I, otherwise there will be a performance penalty. I won't go into detail about it. Why? If you're interested, you can check out blog post on GP Open or watch the GDC presentation. But this is the topic the feature will be about, because the custom feature will validate if the export index is equal to the thread index. So here's an example mesh shader code, and you see export index, and then there's some unknown code, and then we use the export index to export the vertices and primitives, and we want to know if export index is equal thread index. So for me as an AMD dev tech, this is of course a very interesting feature, because then I can just run it on any application that uses mesh shaders to see if the application is following our recommendation or if it doesn't. So the easiest way to start writing your own custom feature is to just copy-paste an existing feature and rename it. So I decided to call it export indices. And since I'm dealing with exports, I just copied the export stability feature because it kind of makes sense, because it's also dealing with exports. On top of this, the export stability feature is a very simple feature. So it's one of the least complex ones. So it's generally a very good starting point. And then once you copy it and rename this, you might have noticed there are 2 projects. So one is the backend project, which is C++ based, and the other one is the front end, project, which is a C# project. And the more interesting one is the backend, actually. So there will be more changes in the backend, and specifically in the feature file. And in the feature file, specifically the inject function. So the inject function goes through the GRIL code of our shader line by line. And it also can inject custom GRIL code. That's why it's called inject function. So our strategy for this custom feature is now we want to catch each vertex and primitive export and then inject for each of them our validation code. So first, we want to catch them. And to do this, we first need to have an HSL to GRIL mapping. Since the feature works on the GRIL level, but we have the shader in HSL, so we kind of need to know the mapping. And so in HSL, the export is like, this is an example code. It's just how we know it, so we just write it out to the export buffers. So there are two possible paths, right? We can have HSL via Dixel and then GRIL, or HSL via SPIRV. So for this presentation, we will only look at Dixel because of like time limits. If you write a feature for your application, obviously you choose the path that your application is taking. If you write a feature and then want to do a merge request and ask Miguel to merge it into the development branch, then you should support both paths. But yeah, today, we only look at the Dixel path. So first we need the HSL to Dixel mapping. And so the Dixel instructions for the vertex export is dx.op.store vertex output, and for the primitive export is dx.op.emit indices. And there's actually also one for primitive attributes export, which I will not talk about today, but it also exists. Once we have this mapping, we need to check if there's an existing Dixel to GRIL mapping. And we have to check this in this specific file, which is Dixel physical block function, and we just search. We have to search if there's an existing switch. And there is one for store vertex output, but there is none for emit indices. So we have to add a new mapping for the emit indices instruction. And the easiest is here again, we just copy and paste an existing instruction, just rename it, just use a similar instruction. So in this case, it's easiest to just copy and paste the store vertex output instruction and then change it to make it work for the emit indices instruction. And while doing that, you should also check the Dixel instruction itself to find out what information this instruction encodes. So here I copy pasted the example for store vertex output instruction, and here you can actually see that the instruction encodes itself already the export index. So here it encodes the vertex ID, and I can tell you the emit indices instruction encodes the primitive ID as well, which is very convenient for us because that's exactly what we're interested in. So now we have the mapping, so we go back to our inject function and just check for this in the visit user instruction, which goes through our GRIL code line by line. And if we find the store vertex output instruction or emit indices instruction, we add the case. And since we are interested in the export indices and we know the GRIL instruction encodes it already, we just retrieve it immediately because we know we need this information. So this is done in this step. Now the next step is we want to inject our validation code. So this is done by our so-called emitters, and they work as well on the GRIL level. So our GRIL validation code will be in this pre-block, and if this validation says, okay, everything is fine, then it will just resume with the original instruction, which in our case is, for example, store vertex output or emit indices. If the validation detected that the export index was not the thread index, then it will emit a message to the front end so that the user will get notified. So, but let's work on this pre-block now. So this is the validation code. And this is done by emitters, as said, so this is our emitter. And then we need the export index, the thread index, and not equal. So we have to write this in GRIL using the emitter. The good thing is we already have export index because we already got it from the visit user instruction from the store vertex output instruction or the emit index instruction. So we only need thread index and not equal. So how do we get thread index? So the first course of action is that we just check emitter and see if there is a function that provides this information. It doesn't, but it does something close. So there is a kernel value that has a mapping to dispatch thread ID. It's not exactly what you want, but it's really close. So what we can do is we just add a new mapping in kernel value for flattened thread ID in group, which is what we want. So it's, again, kind of like a search, copy, and paste job. And then the next missing key is the unequal. So again, we go to emitter, check if it already exists. And in this case, we are lucky because it does. So now we have all three components that we need to write our GRIL code. So it's pre-not equal export index, and then pre-kernel value flattened thread ID in group, which is the thread index that we are interested in. And that's all for our pre-block. The next step is to have an emitter for the failure message to the front end. And for this, we need a new emitter that sets up the message. And here, again, the easiest is to just use what's already there, because this export emitter is used by every existing feature. So since we copied from the export stability feature, we just use the existing emitter that sends the export message. So we can modify it, of course. So in this XML file, you can add variables sent to the front end. So the export stability has a variable to detect if it was a non-error or an infinity error. We can add our own ones. Important is that you need at least a padding, so you cannot just remove all the variables here. And then you can go to the front end and also decide what message you want to write. So in this case, I just wrote export index is not a thread ID. So it's literally just a string you insert there. And that's it. Now we have our custom feature. So you can see I called it export indices, and then it detected that since I was using thread index plus 32 as export index, which is not equal thread index, so it detected it and reported it as an error. And that's really all about to write the custom feature. It's very simple, but it should give you an idea about the workflow, what's needed if you want to write your own. And now I hand back to Miguel, who will talk about tomorrow.
So, yeah, again, let's talk about tomorrow. And specifically, I want to first talk about the next release, debugging, and profiling. So the next release, upcoming release, as part of it, as discussed and implemented by Lou here, we're going to add full mesh shader support with fast path validation. On top of this, the Waterfall feature is finally landing, and that's adding the detection of address scalarization and missing non-uniform resource indices. And it's going to be reducing the granularity of initialization and concurrency validation to a per texture level. Prior to this, it used to be on a per resource level. It's insufficient. And with that, as usual, there is a mountain of improvements, bug fixes, etc. There's a lot of good things in there. But looking ahead, I want to provide full-fledged in-shader debugging. But not in a typical sense. I want to give you what I call live breakpoints. Shader execution is not stopped. Imagine, if you will, a post-processing tone mapping pass that is transforming color spaces, but something's going wrong, right? And you suspect that one of the transformations is producing invalid results. So you hover over a variable, color in this case, and Reshape will recompile the shader typically within a few milliseconds and visualize exactly what this variable contains across all threads. In this case, conveniently as a texture. And turn the in-game, and the texture changes, right? It's live. Think of it as a live way of unboxing the GPU and seeing exactly what it's seeing at that point in time. No emulation, no nothing. Another one is a staple of the CPU world, assertions, right? In this case, let's pretend we can validate GGX roughness. This requires some source integration, but I think that's just fine. And what about profiling? What if you could expect branch coherence and coverage in real time? As before, it's live. Turn the camera, play the game, and watch the different branches light up. Get a different feel for what's happening. On top of this, Reshape may also provide branch timings in real time to figure out where the shader is really spending its time. some challenges in here, but there's a lot of really useful information that could be extracted. So yeah, to me, instrumentation is not something niche. I think it has the potential to be part of everyday development. I think it's a rather unique way of unboxing the GPU. That said, there's a long road ahead, right? A bunch of features plans, ongoing stabilization efforts, the typical. We are a fully open source collaboration, so if you have any issues, proposals, general discussions, critique, feature merges, etc., reach out. I'm going to answer, usually within the same day. And finally, I want to provide a genuine thanks to AMD and Avalanche and all the great people within, and for this collaboration, and my employer, Strike and Distance Studios, for their flexibility. Thank you. So, questions and obligatory legal disclaimer. You.
Me. Thank you a lot for the talk. Really exciting stuff.
Thank you.
I can't help by asking a very provocative question. So, how bad is Unreal Engine 5.4?
Oh, I don't know how I can answer that question. You know, I mean, there's things, there's bugs, you know.
I mean, let's restate. Can you run it on Unreal Engine 5.4?
I can. Yeah.
And see
Oh, 5. Okay. Yeah. So I recently fixed some issues in 5. So actually, on the GitHub page, we have a list of officially like tested and validated titles, and Unreal 4 is there. I need to double check if 5 is, but I ran it like last week. As Lou mentioned, we have a lot of branches. If you want to be on latest, which is where the fun stuff happens, it's the development branch. And if you get a crash, which is really fun, send the GitHub issue my way. I'll fix it.
But in other words, you can just launch it and see in all different shaders. And then if this is super exciting, and then a follow-up is, can you somehow make it work with shader nodes?
Ooh, that's an interesting question. Right now with the shader nodes, I've tried this. I took like an IBL texture, read it out of bounds on purpose.
Right.
I mean, it'll point to the generated HLSL.
Yeah.
You know, readability is a bit iffy. You get like local 171 or something, right? That's an error. There is no trace back there. It's a really interesting question. Maybe if you could provide in-source, so HLSL, annotations like a comment or something that I could pick back up on, yeah, it would allow for like custom, you know, middleware type integration into like the material graph. That's a really cool idea. I like that. I'm gonna try to remember that. Thank you.
Thank you once again. Really excited to try this out.
Thank you. We have one at the front here, or.
I have a question. So, what is the performance overhead when you?
Yeah. So this is
validate?
something we're continuously working on, and the answer is it depends a lot on the title, what it's doing. It's real time, and this is reported actually by a lot of people from AMD. Some titles are a little bit heavier. The thing is, depending on, for example, for Vulkan, it's very like objects, image view object, this and that, bind that, and I can just like wrap them. But for the X12, it's a lot of random GPU virtual addresses, and I need to perform like binary searches every time you do that. So there's a lot of like challenges here. That said, so on actual numbers, I don't know actual numbers, but for a lot of titles I've been playing, it's like I can actually play the game, and it's like 30, 50, 60, you know, so it's doing it. But it depends on the instrumentation you're doing as well. Resource bounds, export stability, super lightweight. Concurrency initialization, not so much.
Okay, thanks.
Yeah, no problem. Yeah. Oh, there's.
Thank you. Thank you for the presentation. So the quick question, how complete GRIL is?
Yeah, so again, it's not a complete abstraction because that would be crazy to implement all of that. What it does is that it exposes, and I'm quoting myself, what I call a meaningful subset. So that's kind of like sample operations, loads, address chains, yada, yada. They're added, like whenever I need something, whenever a feature needs something, I add them. But of course, just because an instruction isn't exposed in GRIL doesn't mean it's not going to compile. It basically has the concept, and this is something I really burrowed deep into GRIL, is that of unexposed instructions, operands, etc. It'll kind of just work. Even if you reference an unexposed instruction, like the result of it, like I don't know what it is, but I need its value, that'll work. It'll just work. You at least know the type it's returning. Like, hey, something specific is returning a float 4. Cool, I'll mess with it. So that's fine. And again, if you modify an image load operation in SPIR-V, there's a lot of like additional operands you can pass to that, and I'm not going to like expose all of them. Even if you modify the instruction, it'll preserve any additional metadata about this instruction for you. You just kind of need to, you can modify it. You can just modify it. It'll preserve it.
Thank you.
Thank you.
So this works on NVIDIA and Intel too?
Intel, yeah, it should. I mean, pretty much every vendor, like it's written within the walls of the specification of Dixel, excuse me, of DirectX and Vulkan. Again, that's it. If there is any issues, send them our way. We're prepping for the next release. We'll fix everything.
Okay, and second question, because I know that you have like a generic assert on your roadmap, but is there any way to just hack me in its current form, just to trigger some macro in shader to trigger some of existing features?
You mean within the reshape stuff or in general?
I mean, to give you an example, right now, like when I want to trigger an, let's call it an assert, right? I just reinforce invalid memory and I have a GPU crash and I use per vendor settings, right?
Yeah.
But it doesn't always work. It's kind of iffy for me. But if I, instead of triggering a GPU crash, if I could currently, in the current form of your software, write a macro that triggers some of the features that could be visible in your UI.
Oh, that's really clever. Okay, yeah. I mean, that'll work. I mean, you can have a buffer, a 1x1 texture buffer, write index 2, and instrument with resource bounds. That'll work. Yeah, okay, that's clever. I like that. Yeah.
So how far is ray tracing support coming? Because this is what I really need it for.
Completely forgot to mention that. We even talked about it. I was going to mention it. So ray tracing right now. So mesh shaders landed before ray tracing. The challenge for me with ray tracing is the local root signatures. Those are a picky thing. Now, one note is that inline ray tracing in compute shaders, pixel shaders, yada yada, are working. Like this, that's just fine. But a fully pipelined ray tracing, pipeline. Right now, it's not going to instrument it. It should let it through. Your game should run. But there's a major caveat. If you initialize a resource in a ray tracing shader, I won't have visibility on it right now. So you might get like, uninitialized resource read on ray tracing output texture. But that's not true, but it's just because there's no support for it just yet. But I mean, it is definitely on the roadmap. I would go as far as to say it's going to be part of like the next, not this release, but the next release. Because it's such an important thing.
So I'm not sure I fully get it. If I don't use local root signatures on a ray generation shader?
No apologies. That is an implementation detail. Basically, fully pipeline RT, PSOs, not today.
Okay.
It's more that the reason why not today is the local read signatures. I need to figure out how to do that.
Okay, thank you.
No, thank you. Going once, going twice. All right. Thank you so much, and awesome questions.